Namaskar, my dear friends. So we have been seeing switching regulator training with examples from data sheets. So let us take one more example, which is LT8604. Okay, so this is a synchronous switching regulator, and what we'll do is we'll go through the data sheet completely and how quickly we can get all the informations that we need to design the circuits, right? So as you can see very quickly, this particular IC, which is LT8604 or LT8604C. So this has the application in industrial sensors. So basically all the sensors like pressure sensor, temperature sensors, or proximity sensors and all those things, they will be using this kind of switching regulators. Even industrial internet of things, or we have like current loops or flow meters, or automotive housekeeping supplies. Basically automotive, like low end applications are there, so they are going to utilize this particular IC. Now what is the main thing that we are going to do with this particular IC, and what benefit we will be getting is, first of all, you have to understand regarding the converter design or DC to DC converter design. Basically what is the input voltage, okay, then what is the output voltage required, or what is the current rating that we need, then how we can select the input capacitor, how we can select output capacitor, how we can set the output voltage regulated using the feedback voltage pin or feedback resistor divider design, okay, and at last we'll be designing the inductor selection methods, okay, and if there is a possibility we can have soft start possibilities or something like that, okay. So this is the benefit that we'll be getting, like let's say around like 30 to 40 pages of data sheet from this particular IC or any other IC. If you take, you have the number of pages around 40 pages or 60 pages or something like that. So within 1 hour or less than an hour, let's say around 30 to 40 minutes, you will be able to understand complete design and what is the information that we need from the data sheet, that you will be able to identify very quickly, okay. So in the data sheet itself, it was given like one of the typical application. So very first thing that you have to do after selecting your the right candidate, maybe like right part number, you have to see the typical application which is given in the first page itself, okay. So let me open the data sheet for you. So as you go into analog.com, let us say for example, we can type in the search box as LT8604, okay. So once we type this, we will get this particular page which is called home page for this particular IC, okay. So as we can see here, we have high efficiency 42 volt 120 milliampere synchronous bus regulators, okay. Now the thing is, you can see this is some of the images that is given, like this is one of the typical circuits. This is the part, footprint, or I mean pin configurations, like in this is DFN package. Similar to that, this is LQFN package. This is the efficiency or something like that. You can see that efficiency is more than 85% for even 36 volt. For 12 volt it is reaching more than 90% for. So that's the understanding, okay. Most of the information are given here itself. You can go through features so that you don't have to get into problem later on. Once you understand all these features and additional details and what is the applications, it helps us a lot to select our right candidate for the application, okay. So here is the data sheet. Once we open this particular data sheet, we will get this particular page, okay. So in this page, very first thing I'll just go through, like we have 28 pages of like data sheet. I will go through one by one. What are the things we need to see to design our circuit, right? So very first thing that we should all understand is, this is the part which is called as features, okay. So features, you go line by line each one of them. Unless you understand this, do not proceed after in the data sheet, okay. So once you understand this, you will be having enough ideas like what kind of features this IC is having. Not only this, any other IC, if you take the same process, you have to follow, okay. So features, all the manufacturers are giving actually their features of this particular IC. where they can be used, and what is the like ISO certification or IEC certification, UL certification, TUB certification, like all those things. Let's say I am telling about ISO, IEC, then UL certification, TUV certification, let us say AEC, that is generally used for like automotive applications like AEC Q100 or Q200, something like that. So all these will be mentioned here itself in the first page. Okay, later also it is mentioned in detail, but this is very good place. Now coming back to features. So as you can see, it is high efficiency 2 megahertz synchronous operation application, and it has more than 90% of efficiency at 50 milliamperes of current output from 12 volt input to 5 volt output. So they have checked one of the application. So if you are going to utilize for 5 volt output application, and you can achieve more than 90% of this. Okay, we have pin selectable forced continuous or burst mode operations. Basically you have two kinds of operation. One is continuous mode operation, one is burst mode operation. Generally I prefer continuous mode operation in our design, so you can also go ahead with that. We have ultra low like quiescent current, which is going to be less than 2.5 microampere, and we have ripple less than 10 millivolt peak to peak. Okay, so you have a very good accuracy as well. As you can see, the input voltage range, so it is going to be from 3.2 volt to 42 volt. So you have application of, let us say, 12 volt input, or let's say 15 volt input, or 18 volt input, or 24 volt input, even 36 volt input. So or even 5 volt input. I mean, let's say you have to design a 3.3 volt regulator, so for that case 5 volt input should be sufficient. So basically this is the voltage ranges that you can utilize at the input to get your any kinds of output. Okay, we have a switch on time which is just 35 nanoseconds. In 35 nanoseconds you will be able to get your output immediately as soon as you start. We have adjustable and synchronizable switching frequency, which is going to be 200 kilohertz to 2.2 kilohertz. So basically uh, there are two ICs. One is uh, LT8604, so that is having adjustable version, as well as synchronizable. If you want, like basically you want to connect it through the external oscillator or external clocks, then you can use LT8604C. Okay, coming back to the enable pin, so it has accurate 1 volt enable threshold. So 1 volt you need to have, then only you will be able to switch on this particular IC. And we have adjustable hysteresis also, that is there in LT8604C only, right? It has internal compensation, it has output soft start, like you can have a soft start capacitor to program your soft start timing and tracking. And at the same time it has two packages. One is LQFN package, which is of 12 pin, and one is a DFN package, which is of 10 pin. Okay, so DFN package are having more heat dissipation by default, I think. So we'll see that as well. Then this is very much suitable for your automotive application, which is LT8604. So as you can see, you have a lot of application that we will see. Now let us quickly move to the other parts of this section. So as you can see, we have general description. So quickly, if you want, you can go through like what is the voltage ranges, what is the frequency ranges, and what are the different modes that it is used. Okay, and what is the power good flag signal that is going to come up. So those things are there, right? Now you can see very quickly here it is. We have LQFN package and DFN package, and in DFN package we don't have synchronization or hysteresis, and we have, but it is 150 degree centigrade grade, but that is, it can be utilized in your automotive applications. Okay, good. So this is the thing that I was talking to you. In the first page itself you have the impression of this particular IC, like how complex it was going to be. So as you can see, we have just one C input capacitor, C output capacitor, one inductor is needed, and like R1 R2 will be required to design our voltage regulated voltage. Okay, and one frequency setting resistor. So this is more than enough, and one capacitor will be needed for the internal voltage supply regulator. So that is there. So only these many components will be required. So very minimal number of components are required to complete this particular circuit. Okay. And as I already mentioned in the beginning itself, the efficiency of this particular IC. So as you can see, for 12-volt input, my efficiency is reaching more than 90%, right? And similar to that, it depends on actually load current. So load current, it is reaching up to 120 milliampere, and we are still maintaining more than 90% of efficiencies with a 700 kilohertz of operation. Okay, good. So moving to the next part, take care of this particular session, particular page, which is going to be absolute maximum rating. So absolute maximum rating tells you to understand a particular pin of the IC should not be given more than this voltage, okay, or more than this particular temperature range. Otherwise this may damage, okay, this may get damaged, right? So you have to understand, like, input voltage or like enable pin voltage must not exceed 42 volts. Similar to that, other parts are there, like PG voltage is up to 42, bias pin voltage is 25 volt, hysteresis voltage that is not more than 12 volt. We have feedback pin or tracking soft tracking pin or soft start voltage pin, so that is should not be more than 4 volt. Okay, we have sync mode voltage which is up to 6 volt. Then we have different operating temperature range for different grades. So as you can see, we have E grade, I grade, and CA. So that are going to up to 125 degrees centigrade. So they can be used for, like, industrial application as well as consumer applications. With J, it can reach up to 150 degrees centigrade. It means it can be utilized very easily for your automotive application also. Okay. Now, very nicely it is mentioned here. As you can see, we have pin configuration for DFN package. Okay. So as you can see, in DFN package, we have 10 pins, like input voltage pin, then enable pin, then we have power good pin also. Like, you can take this up pin to understand whether my output is in range or output is in, like, accurate or not, right? We have sort of start pin, we have feedback setting pin so that you can set the output voltage. We have RT pin to set the output frequency, like, what is the frequency of operation, switching frequency basically. Then we have one internal VCC pin which is going to actually have like regulator for the internal functionalities. We have bias pin, and we have switching regulator pin, like SW pin is going to get connected to the switching inductor, and that is going to give you the output. And we have bootstrap capacitor pin also, which will be supplying the higher voltage to the internal MOSFETs. Okay. So similar config, we have one exposed pad also to dissipate the heat at higher extent. So similar to this package, we have LQFN package as well. And here the only change is like one or two more pins are extra, like 12 pins are there. So one is like DNC pin, like do not connect pin is there, and another one is synchronization mode is there. Okay, that's all. Like synchronization mode pin can be utilized for your external clock functionalities. Okay. Like, let us say you have external clock from your microcontroller, FPGA or somewhere, and you want to work with that clock, then you can use that one instead of using the RT pin for your switching frequency. Coming back to the ordering information, you want to have complete part number for your like design, then you can utilize these part numbers. Like you have DFN package, 3 DFN package are there for different temperature ranges. Okay, so you can use this package like E, I, or J package is there. Then we have CA package, which is LQFN package. Only one version is there. Rest others are 3 versions are there. So for automotive application, the only change that will come up is as W will come in the picture. So W part is the automotive parts. But basically, even if you try to use this I package, sorry, this J package, that is more than enough for your automotive application if you wish to have. But definitely you must consult your like expert, or you can put down your exact questions requirements to the comment box so that we can give you the exact application required which IC will be suitable for you. Okay. Coming back to the electrical characteristics, so there are a lot of things that is there, so we don't have to look into all of them, completely. We just will take what is the needed for our design. So input voltage range you have to take into account, like 2.9 volt minimum should be there and maximum should be there 3.2 volt. Basically minimum input voltage. So minimum input voltage is needed 3.2. So you must make sure that your voltage should not reach less than 3.2 volt. Okay. Similar to that, we have feedback reference voltage, which is going to be around 778 volt. Okay. So feedback reference voltage, you just remember 0.778 volt. Line regulation and all you can take up. So line regulation is very good. It is just plus minus 0.002% per volt. So let us say if you want to get a 5 volt output, then you are going to have 0.01 volt, line regulation, 0.01% line regulation of that. As you can see, we have oscillator switching frequency, which is going to be from for this one, like 220 kilo ohm, it is going to set it to 2 kilohertz, and for 18.2 kilo ohm, it is going to set it to 2 megahertz. So basically, the frequency is changing from, frequency range can be set between 200 kilohertz to 2000 kilohertz or 2 megahertz. Okay. We have like NMOS, like on resistance and current and also all those things are not needed now for our design. Our design requires some other parameters. Let me just show it to you quickly. Yes, PG pin has a pull down resistor which is going to be 550 ohm. Okay, so PG pin has a pull down. So even if you leave it open, there is no problem at all. You can, like if you do not want to utilize PG functionalities, you can leave it open. Tracking software is not needed right now. Let us move to the next part. Okay. There are some typical performance characteristics that is shown by the manufacturer itself, like for 5 volt output, in burst mode. Okay. So as you can see, we have output current and we have efficiency. And what is the difference between these two graphs is, one is burst mode efficiency and this is also burst mode efficiency. Okay. I don't know what is the change that they have given. I think both of the graphs are same, so they should not be doing this. One should be continuous mode, other should be burst mode. That would be the scenario. So you just consider this is actually current mode and this is the continuous mode and this is your burst mode. So you can see it is more than 80% even at the input of 36 volt. Okay. Coming back to the continuous mode operation of IC with C. So this is reaching more than 80%, okay, and even more than 90% for input of 12 volt to give you a 5 volt output. And if you talk about feedback voltage pin, so as you can see, feedback voltage I told you 0.778 volt, okay. So that is not like going very down. It is very close to 0.778 volt, like 0.77 volt or 778 millivolt, right? So with temperature variation, it is not varying much. It is very good. Load regulation, line regulation is always required, but since this is very low current IC, so there is no much difference that will come for your current output. So as you can see, it is just 0.05% per volt, okay, and it is not reaching less than minus 0.01%. Okay. Now let's get into the design directly. So once we have crossed this particular typical characteristics, so we can get into the design quickly. Switching waveform, if you see, wait a moment, switching waveform, if you see, you have the inductor current here. So as current is increasing, you can see we have 5 volt per division switching output. So you are going up. As soon as it start decreasing, so it goes down. So this is how you have the front page application for your switching waveforms. Coming back to the pin configuration, as already pin functionalities, I have already told you, like what is the BST pin or say SW pin. So we'll see during the design, like BST pin, you have to connect one 0.47 nanofarad capacitor between this pin and the SW pin. That will be there. That is one thing. You have to connect one capacitor at this particular pin, which is going to be int VCC pin. Okay, and if you have a supply voltage, then you connect it to more than 3.3 volt to 25 volt. Otherwise, connect it to the ground if you don't have a supply, right? Coming back to RT pin and FW pin, that we have already seen, so we don't need to go through again. But since if you are designing from, very first time, you may not understand from the IC pin functional pin configurations. So here is the place where you have to come and you have to read each and every pin functionalities to understand this, right? Coming back to next one. So LQFN package has two extra pins, like one was hysteresis pin. So hysteresis pin, you have to have like hysteresis open drain logic output. So this pin is pulled to ground when enable pin or under voltage lockout pin is below 1 volt. Okay. So this pin can be used to adjust the enable pin or under voltage lockout pin hysteresis. Okay. So we'll see in the application. And one more is DNC pin, which is extra, that is there. This is very important. Like block diagram gives you an understanding of internal functionalities and internal, circuit design that is there for the IC. That this one you don't see actually in beginning or anywhere unless you go into very deep, right? So we have, as you can see, we have input voltage here, input voltage pin here. You need one capacitor to do that job. If you want to set under voltage lockout capabilities or functionalities, you can utilize one resistor divider configuration at the input enable pin, and that will make sure that this is going to have a comparator, and this comparator is going to put the IC into shutdown mode unless this particular voltage reaches more than 1 volt. Okay, so so this is how it works. Now coming back to the RT pin, which is going to set for switching frequency. So as you can see, this is directly connected to the oscillator. So this RT pin, like RT oscillator, RT resistor, is going to set the switching frequency for your IC. We have power good pin, so that is actually through a MOSFET is connected here. So as whenever the power is like output is good range, this will give you the output. As I will just show it to you whether it is going to be high or low. When it is in fault, what will be the option. But this is open drain pin, so you have to must pull up with one resistor, let us say 10k or 100k, anything is fine. Coming back to the soft start, so this helps you to start the IC very softly. Basically, I don't want my output to be very quickly. I want it to be, let's say, slowly reach to the output. Okay, so this is how sometimes it works. This is the feedback pin, which is going to utilize regulate the output voltage by using two resistor divider like R2 and R1. And coming back to this side, we have the bias pin. So bias pin, you can connect it to the input directly or connect it to the output. So sorry, bias pin you can connect it to the output. Otherwise, you can tie it to the ground also if you do not want to utilize this. Okay. We have internal voltage regulator, which is actually used for internal functionalities. That is basically nothing but a 3.3 volt regulator inside internal regulator, so that you can have to just tie it through a capacitor to the ground. We have bootstrap capacitor for the MOSFET functionalities, internal MOSFET switches, so that you have to connect it through the switching pin like SW pin through one capacitor. And this is the inductor that is going to do the switching action to give you the output, and this is the ground pin. We have one exposed pad pin also, so that also is there. So similar to that LT8604, we have LT8604C functionality. So almost both the functionalities are same. We have just to add one more hysteresis at the enable pin. So there you don't have to put only one voltage. You can put one external resistor to have the hysteresis at the enable. And we have sync mode that is going to utilize one external clock to do the job of switching action at a particular defined frequency by the external let's say controller or something. So moving to the next part. As you can see about the operations. Operation is very tedious job to read each and every line and do the job. So I'll just show you what are the things that we need to take out quickly. Okay. So let's keep moving. Keep moving. So once we move down, we have continuous mode. We have application. Good. So this is the thing that we have to take into account. Okay. So the minimum inductor required will be Vout divided by 0.07 into FSW into 1 minus Vout by 40. So let us say we need 5 volt output and we need, let us say, 700 kilohertz. Okay. So in that case, you just put this value in this and you have to make sure the inductor value must be greater than the calculated value based on these values. Okay. So that's the one understanding you have to keep in mind. So this is how, like for robust operation over V input and V output range, use an inductor value larger than this particular L minimum value. Okay. So basically that is the first requirement. So you have a threshold now for your inductor value that you are going to choose. Now coming back to the other things, let us talk about, yes, here, feedback resistor network. Okay. So this formula you have to take into account, like keep it in a note. Like once you are reading the data sheet, you have to have a notebook with you with pen and paper. So what happens is, like, put your L minimum formula, then put your this feedback formula, which is going to design your R1 and R2 values based on this particular value, which is going to be R2 is equal to R1 multiplied by V out divided by 0.778 minus 1. Okay. So according to this, we will be able to regulate your output value which is needed. So that is second one. As you can see, they have recommended that use 1% of resistor tolerance. You don't go ahead with 5% and all, otherwise you will be like losing up the output voltage regulation. Setting the switching frequency. This is also important. Okay. So let's say you don't want to calculate anything. You can directly choose one of the values from this. So let's say if you want to work at 700 kilohertz, like it is megahertz here, so 0.7 megahertz or 700 kilohertz. So use a resistor value of 60.4 kilo ohm. Similar to that, if you want to work ahead with 1.2 megahertz, then you have to utilize 33.2 kilohertz, 33.2 kilo ohm resistor. If you want to work very high frequency, let us say 2 megahertz, you just have to utilize 18.2 kilo ohm. So the advantage of using higher frequency of operation is you will be reducing the frequency of operation. You will be using the value of inductor. Okay. So as my FSW increases, my inductor value actually decreases. Okay. But I'll suggest you, whenever you are designing a particular circuit for your industrial application or automotive application or any, like a I mean, example for that purpose, you just try to be like within the range of like 500 to 1000 kilohertz. That is more than enough for your any application. Okay. So this is a very optimum frequency of switching frequency operation, which where you will get a particular a nominal values of uh, inductor, and you will not lose the efficiency side as well. So this was all about the switching frequency versus RT values. Okay. So as you can see, this one is very interesting. If you want to have a reading about it, they will tell you what is the advantage of having higher frequency operation or lower frequency operation. So as you can see, the selection of operating frequency is a trade-off for what? For efficiency, for component size and input voltage range. Okay. So this is how you are going to affect your design based on the switching frequency that you are going to select. Okay. Good. So switching frequency maximum that you can utilize is based on this particular formula if you want. So generally T on minimum you take it 20%, okay, or 0.2 of your switching frequency, whatever you want. So whatever the switching frequency that you are going to set, you just select the 20% or less than that for your minimum. Coming back to the next part, the input minimum will be required based on this. So that is not needed right now. Just we'll go ahead with inductor selection now. So that was a minimum value of inductor that I told you just before. Now we'll select the exact inductor value that is needed. So what is the thing that we will require? A good start choice for inductor value is V output plus VSW bottom divided by FSW multiplied by 20. Okay. So as you can see, VSW bottom will be 0.14 volt. Okay. So we have output voltage required already, like let's say 5 volt, and let's say 700 kilohertz is required for this, like FSW. So using this formula, you will be having uh, a inductor value calculated. Okay. Now, what will be the current rating of this particular inductor? That is also a good point to understand in the data sheet. So basically, I peak or inductor current peak value can be calculated by I load maximum plus half of delta IL by 2. Okay, like half of delta IL. So generally, delta IL is taken to be, let's say, 40% of your I peak. Okay, or 40% of the inductor maximum current that is required. Okay. Now coming back to the calculating the I out maximum. So I out maximum will be I limit minus delta IL by 2, and I limit value will be like limited by the MOSFET limits that is already given, and like in top switch I limit is at 185 milliamperes, that is there. So you have to set I limit as 185 milliampere for low duty cycle or decreases linearly to 137 milliamperes. Okay. Good. So these are the things that we had to require to find out this particular thing. Understanding. Now L minimum again, if you want, you can finally put this part like after two formulas of inductor selection, you can utilize this particular formula to calculate your minimum value. So see, good choice was multiplied by 20, but minimum value if you want to utilize so that you reduce the space or reduce the size of the inductor, you can multiply even by 12.5. Okay. But for duty cycle greater than 50% only, it will be used. Otherwise, for higher range or lower range of duty cycle, if you want to use, sorry, lower range of duty cycle, if you want to use, you have to use this formula itself. Okay. So I'll suggest you to go ahead with this. No need to use this particular specific operation. Okay. Good. So input capacitor you can utilize always. I prefer always to go ahead with X5R for bigger values of ceramic capacitor. Okay. Otherwise, for a smaller values, if you have to use, you always go ahead with X7R. That is very like sufficient and very prominently available in the market. There is no problem at all. Similar to that, if you want to use a bulk capacitor, you can go ahead with low ESR electrolytic capacitor as well, like aluminum electrolytic capacitors are there coming these days with low ESR values. So in addition to that, you have to use some 0.1 microfarad capacitor as well. So C input capacitor is done. Coming back to the output capacitor value you can calculate with this. So I will suggest you always to go ahead with C out greater than the value that is calculated with this. Okay. So you can go ahead with 50 divided by V out into FSW. So as my V out is increasing, my output voltage, output capacitor requirement is decreasing. Okay, that you can understand. Similar to that, as my frequency of operation is increasing, my output capacitance value is also decreasing. So that you can see, right? So this is the another understanding, like we have identified our output capacitor as well. Now coming back to the next part, which is going to be capacitor. If you want to use a very easy design, you use at the input in like electrolytic capacitor in addition to ceramic capacitor. Similar to that, output capacitor also you have this configuration, that is more than enough for your design. Coming back to the ceramic capacitor side, so because you have a space constraint or something like that, in that case you can utilize ceramic capacitor of little lower values also, but like 100 or 120 microfarad should be enough for your input capacitors. Now, enable pin or under voltage lockout pin, if you don't want to utilize any enable pin like under voltage lockout functionalities or something like that, directly connect your enable pin to the input voltage. That is more than enough. Okay. Or otherwise, if you want to utilize that, then you can use R3, R4 values to the, like let's set this like this, R4, R3, and this is your enable pin, and this is your input voltage. Okay, so designing the, and you put it to the ground. So designing these values of R3 and R4, you can utilize this particular formula. So let us say you have a 12 volt to 5 volt regulator design required, and you don't want this regulator to work below 10 volt. So you can use this V input enable under voltage is 10 volt. So 10 divided by 1.04 minus 1 multiplied by your R4 is going to give you the value of R3. So the IC will not start below 10 volt. Okay. So as you can see, for 5 volt output, we just need let's say around 6 volt input, and it will start working. So as soon as my input voltage started 6 volt, you had got your output voltage. But the thing is, you don't want to get the output unless it reaches 10 volt at the input. So for that case, you are restricting that using the under voltage lockout design. Okay. That's the meaning that you have to understand this. What we are going to do is we are going to restrict the output voltage by designing this under voltage lockout voltage divider circuit. Good. So there are like rising voltage, and there is falling voltage. So as you can see, rising voltage will be a little bit higher, and it will not switch off until it reaches below this particular voltage. Otherwise, again immediately it will switch off, then problem, right? So that's the reason we are going to design the hysteresis. Coming back to the int VCC regulator, so we have one internal load dropout regulator which produces 3.4 volt supply from input voltage that powers the drivers and internal bias circuitry. Okay, so this is the place where you will be required one capacitor. We have output voltage tracking and soft start as well. So soft start, if you want to configure, then you can put one capacitor at the SS pin to the ground. So I'll tell you, like we have here from 0.0 volt to 0.778 volt. We have the track or soft start voltage will be override, and the internal voltage will be this much. And when a track and soft start voltage is above this, then tracking is disabled. Okay, and the feedback voltage will be regulating the internal reference voltage. So that's the understanding we should have. Good. We have power good operation. So power good operation, as you can see, the what happens is I'll just tell you what is the main functionality of power good. So we have the feedback pin, so which was 0.778. So my my output is regulated whenever the feedback voltage pin is around this voltage. Okay. So what it says is when the feedback voltage range is 0.720 volt to 0.836 volt, the output is considered to be good, and the open drain PG pin goes high. Okay, high impedance. Okay, goes high impedance and typically pulled high when an external resistor is connected. Okay, so whenever this is between this range, PG pin will be high. So you have to just keep a you have to just keep one pull up resistor on this particular PG pin, and whenever uh, the output feedback pin is not in this range, like the output voltage is not regulated properly, this PG pin will be pulled low. And as you can understand, when PG pin is pulled low, then you will see the output is not good, and you will understand that the regulator is not working properly. So this is the very good understanding about power good pin. Good. So this was all about design. If you want to have a reverse protection at the input, what you can do is you can put one Schottky diode or normal diode at the input. But the disadvantage that you may get here is you will be losing around 0.7 volt at the input, or 0.3 volt for a Schottky diode drop. So if you are ready to have a drop at the input, you can utilize one diode for the reverse voltage protection. At the same time, if you are working with battery, then you don't want to have a drop, so you don't put one any reverse protection. That is not needed much. Good. They have given us the complete PCB layout as well. Okay, so as you can see, this is the PCB layout that is given by analog devices. So this is for DFN package and this is for LQFN package. And how nicely they are connected, like where is your RT pin, how you can set your resistor here, then where is your SW pin, and you have to make sure that output is little bit far than this particular inductor. You can see SW pin, inductor is here, we have this output pin here, and we have where is the feedback resistor network. So R1 R2 is here, so you have feedback pin here, R1 and R2 network to regulate your output voltage. Okay, and here we have connected one more feed forward capacitor across this R2 to help you the proper output. We have input capacitor and input voltage. As you can see at this particular exposed pad, it is a ground with a lot of bias, so that is also needed. So this is the understanding how to design a proper regulator PCB design for your requirement. Let's get into the typical application. So what we'll do is we'll just see a very quick typical application here. Let us say our input voltage is 12 volt and we have a requirement of 5 volt for our sensor application with 120 milliampere rating. Okay, so to do this job, this particular IC can be chosen, which is LT8604. Now I'll just quickly tell you input voltage you have already 12 volt, let us say. So at the input what you can do is I'll just tell you this one, let's say put 22 microfarad. Okay, put one more 10 microfarad. Okay, and then put one more 0.1 microfarad. So this will be a good understanding, and put it to the ground. Okay, so 22 plus 10 plus 0.1 plus one more 1 is there, you let it be that also. So 4 capacitors you can put at the input. So Cin is done. Make sure up to 10 microfarad and 1 microfarad capacitors have the voltage rating of more than 25 volt or 35 volt. Okay, then 0.1 microfarad you always choose a 50 volt rating because that is abundantly available. So 0.1 microfarad by default, I have been telling you in so many sessions, we always use 50 volt ratings. Even 25 volt ratings are available, but that is not required. So input is done. Coming back to the output voltage capacitor. So output capacitor, what you have to do is you utilize 10 microfarad is there, one more 10 microfarad is given here. Utilize one more 10 microfarad and let's say one more 22 microfarad and 0.1 microfarad. So this much capacitor you add at the so what you have to add? 10 microfarad, 22 microfarad. Otherwise, what you can do is all these 10 microfarad, you can convert it to 22 plus 0.1. That is more than enough or more than sufficient. One more, one more, option can be use electrolytic capacitor of 100 microfarad. Okay, plus 0.1 microfarad of ceramic capacitor at C input. That is enough. Similar to that same capacitor you can utilize at the output also. That is also more than enough. Okay, now let us say int VCC is a port 0.1, put 1 microfarad capacitor, and then track and soft start pin you have to use 10 nanofarad capacitor. To work with this IC with 700 kilohertz, in the table you can see that it is required 60.4 kilo ohm resistor to work with 700 kilohertz. If you want to work with other voltage, other switching frequency, you have to choose according to the data sheet that I showed you just now. So go there and quickly find out the resistor value for your particular switching voltage application. Based on that, the L value will also change. That's the understanding you should have. Now coming back to the inductor design. So inductor design, L value was there, one formula was there. So use that value to get this particular value. Okay, and you have to make sure the current rating of this particular selected inductor must be more than around twice or thrice of this particular current. So choose by default, like you just close your eye and choose around 1 ampere of rating or around 2 amperes of rating. That will be always sufficient, but that may be little costly, so you can go ahead with 0.7 ampere rating also to reduce the cost of your inductor. Now since it is 5 volt, you can directly pull it up with the same output voltage and send it to a pin which is going to set a microcontroller pin. If you are sending it, Just make sure the output, the tolerant of that pin is 5 volt. Otherwise, connect it to the 3.3 volt in voltage. Okay. Otherwise, what you can do is this PG pin can also drive one LED. So what you can do is put one resistor and put one LED. Okay. So this LED, if it is glowing, then you will understand that the output is within the range, right? Now, last but not the least, what you have to do is you have to design the values of R1 and R2 to get the output voltage of 5 volts. So there was a formula which was there, right? Like R1 is equal to R2 times the output divided by 0.778 minus 1. So put the value of, let's say R2 is 187 kilo ohm, then you will get R1 value as 1 mega ohm. But I'll suggest you to, like utilize some other values also, not a problem. So if you want, you can use R2 as 100 kilo ohm, and accordingly corresponding value of R1 will be calculated and you can use that value. So alright guys, this was all about this particular design. So with this particular data sheet and one application, complete application we have seen. We have lot of other application we'll see in our next session. So hope you have a good understanding like what are the things that is needed from the data sheet to have a complete and concrete design of your power supplies, okay, for different levels. And this was an application very dedicated to sensors application in our industrial application or automotive application, or flow meters and all. So for that purpose, this particular IC I took. However, this has given you an idea of utilizing any other ICs as well for your design, like what are the different parameters that is needed for your design. So if you do have any questions or any particular application that is needed, you can always put down your queries in the comment box, and we shall be able to come up with the exact answer or accurate answer and reliable answer that is always like done by our experts for different clients or different application uh, that is there in our projects. So thank you so much.